Hello and welcome back. This is Raiaan from Roots of Unity, and today we're going to wrap up our lesson on polar coordinates. We're going to look at the applications of polar coordinates, such as finding the intersection, the area under the curve, and the area between polar curves. We'll start off with finding the intersection between two polar curves. It's similar to the method used in any Cartesian graph. Taking R as the subject, you equate both the equations together. You can see what I mean in the following example. We carry on with general simplification, such as making sure the angles are the same everywhere. Here, we'll remove the double angles and bring everything to the left-hand side. Make sure you do not divide each side with sine theta. It will remove the value. So then we equate both factors to 0 and find the necessary values of theta within the range. Substituting theta back into the respective origin equation, we'll find the values of r, and hence the points of intersection. To sum it up, keep in mind the range you're working with. Consider every value of theta you find, although they might not seem obvious at first. Use the sketch of the graph as a reference, but also keep in mind that polar and Cartesian coordinates work differently. For example, look at the graphs for cos theta and cos 2 theta. Although it might look like there is an intersecting point at pi by 2, you can see that for cos 2 theta, the value of r there is undefined. So it's always better to double check. Moving on, now we'll learn how to find the area enclosed by a curve. Take a look at a diagram along with the coordinates. Our aim is to find the area ABC, which we assume to be delta A. As delta theta approaches 0, so does delta r. Assume this to be a very small area ABC. It would be a sector with area half r squared delta theta. Once our limit is set, we will use d theta instead. As we add these small increments over an interval alpha to beta, we can figure out the area. The formula is half r squared d theta with a limit from alpha to beta. Now let's look at an example. If you've watched our previous video, you might remember this equation from the curve we sketched. It's the rose. We're going to find its area from 0 to 2 pi. Firstly, let's insert the equation into the formula. Then we expand 6 sine 3 theta with the help of double angle formula. Now, if we take a look at the graph, it's obvious that this same area has been repeated thrice. So we take a limit of 0 to pi by 3 because that's where the first loop ends. Then we multiply this by 3. After integrating and applying the limits, we get a value of 9 pi for the area. Here's the catch. If we alternatively took the limit from 0 to 2 pi at once, we will find the value of the area twice larger than previously calculated. That's because this also accounts for the regions with r less than 0. If you remember, while plotting this graph, we found values such as -6. Therefore, be careful while handling these graphs. Okay, time to learn how to find the area between polar curves. It's pretty similar to how you'd handle Cartesian curves. The formula is half r2 squared minus r1 squared d theta. It is not the same as r2 minus r1 whole squared. Please remember this. The limit may be indicated either by saying over the interval or content between this and the lines theta equals to a and theta equals to b. Now, let's take a look at another example. Here, we have r equals to sine theta and r equals to 2 sine theta. The range is from pi by 6 to pi by 2. Here, we can say that 2 sine theta is bigger, so it goes in first and then we subtract r sine theta from it. We make use of double angle formulas and hence calculate the area. Here's a reminder once again that Cartesian and polar coordinates are not the same. Remember to pay close attention to the integrals you're working with. Let's take a look at the curves of cos theta and sin theta together. Recall what you learned earlier about finding the intersecting points. Although from a Cartesian perspective there are two intersecting points, only one of them is the true polar intersection. The other looks deceiving. You can see that the values of theta are actually different. What we'll do here is consider the limits separately and add them together. Here, I took 0 to pi by 4 as an interval and pi by 4 to pi by 2 as another. Then I carried on with integration as usual and found the area. You should note that this could have also been done as double the first segment, since sine and cos graphs are geometric. In this case, there were no undefined values. Always make sure to take care whilst integrating, especially with limits. So that wraps up our series on polar coordinates. I hope this was useful for you. We managed to cover very elaborate topics under a short time. So thank you once again. I'm signing off for now.